Hi there, and welcome to this demo video, in which we'd like to show you some of the tools that have been developed to support collaborative MDO in the Agile paradigm. In this video we'll give you a small demonstration of the capabilities that have been developed over the course of the Agile project to perform MDO in a large group of heterogeneous experts. My name is Imco van Gent and I'm from Delft University of Technology, and in this video you'll also hear from Benedict Eichner from AGILE University and Riccardo Lombardi from Noesis Solutions. Let's start off with a short introduction on the Agile project to give you a bit more an idea about the context in which this work has all been developed. Agile is a creative acronym that is short for Aircraft Third Generation MDO for Innovative Collaboration of Heterogeneous Teams of Experts. It is a big project sponsored by the European Union, in which a group of 19 different partners work together to develop a new generation framework to perform MDO in large heterogeneous organizations. You can find more information about the project online at our website agile-project.eu. The Agile project ran for 3.5 years from June 2015 to November 2018. And the ambition of the project was to develop technologies that will enable a more agile way of collaboration and joint development and experimenting on innovative aircraft products. The two main quantitative objectives that were set at the beginning of the project were to achieve a 20% reduction of the time needed to converge the optimization of an aircraft configuration and to achieve a 40% reduction of the time needed to solve an MDO problem in a heterogeneous team of specialists enabled by agile collaboration processes and agile optimization techniques. In order to achieve these objectives, many different applications from different partners within the Agile project were combined into one Agile framework. The combination of this framework, along with the methodology that we have developed to have a structured approach to perform MDO collaboratively, is what we'd like to call the Agile paradigm. And in this video we'll highlight some of the key technologies from this paradigm that will help you to set up an MDO system and also execute it in different workflow softwares. The remainder of this video is divided in 3 main parts and will end with a summary and conclusion. In part 1 we'll tell you how to set up a collaborative MDO system the Agile way. Then in part 2 we'll tell you how to formulate MDO problems and different solution strategies to solve those problems. And in the last part, we'll show you how you can create executable workflows in different workflow engines. So let's get started with the first part. In this part of the demo, we'd like to show you how you can set up a collaborative MDO system using the Agile methodology and technologies. We'll use a small example for this, and at the end of this part, we'll also show you where you can find an open source repository that we'll use throughout the rest of the video as well. Let's consider the situation that is shown on this slide. Here we have 4 different typical aircraft design tools available that can be provided by 4 different partners from the Agile project. Furthermore, we have a 5th partner that would like to use these 4 tools to perform a multidisciplinary design optimization. Note that from the point of view of collaboration, we are really in a challenging situation over here, since we have 5 different partners that are at 5 different locations all over the world. But we would like to use their tools in one MDO workflow, and their tools need to be executed many times probably. So how can we set up our MDO system such that we can run the tools from these 4 different partners in one workflow that is executed by the TU Delft? In order to build such an MDO workflow, we first need to establish how all these different tools are coupled together. For example, we would expect that the aerodynamics tool is providing some loads that are used by the structures tool. And there might be more of such couplings present in the system that we need to establish correctly in order to run the correct MDO workflow at the end. One way to establish these couplings would of course be to connect the tools manually. We might be aware that the aerodynamics tool is providing the lift forces and that these lift forces need to be coupled as input to the structures tool, as is shown over here. However, establishing the couplings in this manual way will make it very hard to maintain our MDO system. Because if we get more tools in the system, we will get a very cluttered web of interconnected tools, as is shown on the top right of the slide. So instead of using these manual connections and direct couplings between the tools, we need some other way to define what are the inputs and the outputs of the different design competences that we have available. The way we do this in Agile is by letting the tools first speak the same language. And this language is called CPEX. CPEX is an XML schema that was developed by the DLR, which allows us to store a lot of typical aircraft design data in one single file. For example, we can store the full geometry of the aircraft in the preliminary and conceptual design stage, but also typical results of structural and aerodynamic analysis. On the right, you'll see the top-level elements of the CPEX schema, and you can find the full schema at the open source repository that is shown on the slide as well. Coming back to our small example of the lift forces that were connected between the aerodynamics and the structures tool, we now have to approach things a bit differently. The aerodynamics tool now needs to write a CPEX file, and it will have to write these lift forces into that file. And at the same time, the structures tool needs to be able to read the lift forces that it needs from the CPEX file, and will have to translate those forces to its native format. In short, we have to CPEXize our tools, and we have to add CPEX readers and CPEX writers to every design competence in order to be able to set up our collaborative MDO system. If we then look at the full system, we also see that we have a much cleaner approach now. We simply ask the different tool providers to let their tools speak CPEX by adding a CPEX reader and a CPEX writer, and in that way we now have connected all the tools indirectly through the central data schema, as is shown in the top right of the slide. Let's now have a look at the tool repository that we have available and that we'll use throughout the rest of this video. The design competences that we'll use in the rest of this video to build the MDO system are based on a problem that was originally developed by NASA. This problem is called the supersonic business jet, and it's a typical MDO benchmark problem that is used in many papers. The French aerospace lab ONERA has developed an open source OpenMDAO implementation of this problem, and based on this repository also an agile implementation of the different design tools have been developed and can be found online. In the rest of this video we'll use this Bitbucket repository, which you can also install as a Python package using the command pip install ssbj-capmos. Now let me quickly show you this repository so you have a bit more an idea on what it is. If we follow the last link on the previous slide, we end up at this open source repository on Bitbucket. Here you can already inspect the supersonic business jet tools that we have, and you can also clone or download them to your own system. Alternatively, you could also use pip install to install the package to your local Python installation. Of course, you need to have Python installed and also pip in order to do this. But if you have these installed, you would go to a terminal and simply do pip install ssbj-capmos. And this will install the supersonic business jet repository and also all the other packages that are needed for this repository. If we now go to our local Python installation, in this case I installed it in Python 2.7, we can go to the site packages and we can find there the SSBJ repository. Now we can also have a closer inspection of this repository, and we see that the different tools have been installed. For example, we have our aerodynamics tool here, which is simply a Python file that does the aerodynamic analysis. If we want to test this tool, we would open a terminal inside this folder. And then we can simply test the aerodynamics tool by doing Python aerodynamics.py with the argument test. If we run this with the test argument, an example input file will be created for the aerodynamics tool. The tool is executed and it will create an output file. And we see the results in the same folder. So here we have our aerodynamics input file, which is simply an XML file containing all the inputs that are required to run this tool. Note that here we are not really using the CPEC schema, but we have made our own smaller data schema for this small demonstration case. But you see here that the Mach number, the flight level are all inputs for the aerodynamic analysis. And after the tool has been executed, we also get our output file containing the results that this tool has been calculating, like the lift, the drag force, lift over drag, and the pressure coefficient. So as we have just seen, we now have a repository available with different design competences that we can use to analyze the supersonic business jet. These competences have been CPEC sized, so they are able to read an XML file for their inputs, and they will write their results to another XML file. However, the question still remains how we can now establish the couplings between these different tools, and how we can formulate different MDO problems and solution strategies using these tools. This is the subject of the second part of this demo video, which will start right away.
Hi there, my name is Benedikt Eigner from Aachen University, and I would like to welcome you to the second part of the tutorial video, in which I would like to show you how to formulate MDO systems and solution strategies. To help you do that, the AGILE project has come up with a set of tools which have all been merged together in one web service called the MDO system interface. I would like to give you a short introduction on the capabilities of the MDO system interface and how to use it, again based on the supersonic business jet example from earlier. To get the system interface web service running, all you need is an internet connection and a browser. Then go to mdosysteminterface.agileproject.eu and you're ready to go. We are now on the starting page of the MDO system interface. Here you can find some example files that you can download to get started formulating your MDO problems. The first one is the Seller problem, which is a simple and well-known example in MDO, and the second one is our supersonic business jet. You can easily download the example files here and store them on your local file system. Now, to start a new session in the MDO system interface, just click this button and you're ready to go. Now the MDO system interface comes with three different visualization types. The first one is the extended design structure matrix, the second one is the edge bundling diagram, and the third one is the Sankey diagram. All of the three visualize the same MDO system data, just in a different way. As already mentioned before, the package is a combination of different technologies developed within the AGILE project. The first one is CATMOS, the knowledge and graph-based agile design with multidisciplinary optimization system. CATMOS is the system that performs all the different formulation steps using graph theory. It's been developed by TU Delft and is programmed in Python. It is open source, so please go check it out clicking the button below. The second technology is Commandos, the common MDO workflow schema. Commandos is an open source XML-based storage system for MDO system data. All the underlying information on your MDO problem formulations and solution strategies is contained here. And last but not least, Vistems, the visualization tool for MDO systems. Vistems is the graphical user interface that allows you to easily formulate MDO problems, find a suitable solution strategy, and inspect your MDO systems. It is part of the CATMOS repository and can also be used locally via pip installing CATMOS. Okay, so if you want to open an MDO system, simply click on the Open button here. And what we can see now is that there are no graphs to inspect yet, which is because we simply didn't do anything in the MDO system interface yet. And to upload a graph or create a graph, we can use the Add button on the right. And we have different options here. We can upload KDMS files, which is the native format of Catmos. We can also upload commandos files or entire databases. And we can also create an entire graph from scratch using our own tools and specifying everything by ourselves, which we will do now. And the new graph will be called SSBJ RCG, since it is the repository graph of our SSBJ example. And basically it will contain all the tools that are in the Supersonic Business Jet example, which is the 4 tools that have been shown before. And I will always be using the XDSM view, because this is the only view in which you can actually manipulate your MDO systems. The other 2 are good for visualization, but you cannot change anything in your MDO system in those 2. So let's open the XDSM view and see what we can do here. And now that we have initialized our first MDO system, we can start adding competence blocks to our repository step by step. And right now our system is very empty. We only have this coordinator here, which is basically the outer world of our MDO system. And I will start adding design competences now by clicking this plus button here. I have 2 choices. Either I can upload a design competence or a mathematical function, but I will start with the design competences of the Supersonic Business Jet example. My first tool will be the error analysis, which I have to specify a name for, and then also I have to upload an input and an output file that I have previously created somehow. And those files, they basically have to be XML files, so that means you have to follow the XML schema rules. In this case we have, for example, a data schema, an aircraft element, some geometry and weight specifications, which basically contains the entire data set of our aerodynamics input XML file. The output file basically looks the same with other variables, of course, but we have to follow the same data schema for the entire MDO system. Otherwise, Catmos will not be able to make those tool connections, and your tools will not be able to communicate with each other. So it's very important that you follow those same data schema rules for all of your competences. In Agile, for example, we are using the CPAC schema, but you can use any other XML schema that you want. You can come up with your own or use pre-existing ones. Okay, I will upload these 2 XML files, aerodynamics input and output, and once I submit it, I can see the error analysis competence block has been added to my MDO system. Now the second tool that I will be adding is the structural analysis. It's also a design competence. And of course this one has also 2 files, 1 input and 1 output file of the same data schema. And on submitting this, I can actually see those 2 competences are in some way connected to each other. So we can see that the error analysis writes 1 output to the structural analysis, which is basically the loads, the lift force of the wing, and that way the structural analysis is able to calculate the structural mass of the wing. And vice versa, the structural analysis is also giving 2 output variables to the error analysis, which is the theta and the WT. And of course I can also open this MDO system in the other 2 views. By clicking this button I can change the visualization type. For example, I can have a look in the edge bundles view, how it looks there. Well, in this case the circular layout out between those 3 tools is not very fancy yet, but basically I can see how the tools are connected to each other. And the same I can do for the Sankey diagram. which basically looks like this. I can have the tools reorganized according to what I want, and I see the green arrows are always the tool outputs and the red arrows are the tool inputs. And the magnitude of the arrows gives me how many variables are actually in this connection. So if the arrow is wide, it means there are a lot of connections. If the arrow is narrow, then there are only few connections between the tools. Okay, I'll go back to the XDSM view, and I can also have a closer look at the competences themselves. For example, for the aerodynamic competence, I can quickly see what is the competence information. I can right click on the competence block and see the metadata for the error analysis. And since we've just created this tool, everything is empty here. I could add a description, whatever I would like to give as a description. I could add a status, for example, is it available or not? Say yes, it's available. I can also specify an owner, a creator, and operator of the tool, so who's actually executing it, who created it, and who's the owner of it. But I cannot do anything here yet because, well, there are no people involved in our MDO system yet. So basically I will have to create them first. And I can add team members to my MDO system by clicking this button here. I can see that there are no people, no contacts involved in the MDO system yet, so I will have to add a new contact, and I will just add myself. Give myself an ID. And the function, country, company, I will leave those things out for now. And in this MDO system, I am the architect as well as the integrator, and let's say I'm also a tool specialist. I'll have to specify an email address to make the connection later between the tools. If we want to execute the tools remotely, then we would also have to specify an email address so the other tools in the workflow can actually find myself. Okay, I will add myself, and now if I go back to the error analysis tool and see for the competence information, go to available, and then as an owner I can actually add myself, as a creator also myself, and I'm also the operator of the tool. I can of course specify more information such as performance, what is the precision or the fidelity level of the tool, what's the runtime. I can give some license information and some links to repositories or downloads for the tool as well. Okay, I will just do that right now, and that's done for this error analysis tool. I can also do this for the structural analysis, of course. I can now add my competence blocks step by step and therefore create my MDO system and build it up the way I want to. Of course, this will take some time, so what I will do now is I will just add the entire tool repository that has already been previously done, so I can show you how to further manipulate your MDO problem. We'll upload this as a commandos file, the RCG, that's the correct file. When I submit that and open it, then we can see that this tool repository containing all the 4 tools, error analysis, structural analysis, performance, and also propulsion analysis of the supersonic business jet are included, and also those mathematical functions and constraints that have been additionally created are also there. Now what we can see right now is that these tools are kind of arbitrarily ordered, so there's no real tool order yet. In a normal aircraft design problem, we would always expect the performance analysis to be at the very end of our analysis. The error analysis would basically be somewhere in the front, as well as the structural analysis. But in this case we see that there's really no order of the tools yet. And I will now quickly go through the graph inspection and graph manipulation options that you have to build up your MDO problem formulation in a feasible way, to show you and give you an idea how this would work. And now to inspect and manipulate my MDO system to make it a problem formulation, I have two main drop-down menus, the graph inspection and the graph manipulation. And I would like to start with the graph inspection, where I can have a look at my graph in more detail. For example, I can find specific graph elements that I would like to have a closer look at. In this case, I will quickly show you how to search for them. You can find it out yourself, the details, but basically there are two categories: variables and functions. In this case, I would just like to have all the functions that are in my MDO system. So as a subcategory, I give all, and then I will get a list of all the competence blocks that are in my MDO system. I can also see them on the diagonal. And yes, this list can be filtered by just typing in what I would like to see. In this case, performance analysis. In this case, since it's a very small MDO system, it's not very necessary to do that, but once the MDO system gets very big, it can be easily 1,000 variable connections and hundreds of tools. It makes a lot of sense to do that. And I can also have a closer look at my data schema, my data model that I had previously already shown in the XML files, by using this option here. And there are two different layouts or views that I have here. One is a tree view and the other one is a list view. And I have also different variable categorizations. There is, for example, the schema, which is the basic XML scheme that I already showed you. And then there are some others like node levels, function levels, that I won't go into detail on right now. But basically, they're just a different way of categorizing your XML schema. So let's start with a basic tree view of the XML schema. A window will open, and we can see the data schema node again, and it apparently has 55 nodes downstream. If we click with the left mouse click, we can expand or collapse the schema. There's the aircraft node again. We'll open that one. Then there's the other, where we can see the drag and the lift forces again that we have previously already seen in the connection between the aerodynamic and the structural analysis competence. And by right-clicking on this lift node here, we can further inspect this in detail. We can, for example, get some information about the node. We can see the name, the XPath, and the data schema, the type, the level, and also the value, which is currently unknown, but this could be any value for the lift. Then we can also download the tree view as an XML file. So this schema that we're currently seeing, we can download this to our local file system like this. And we can also do some other inspections. For example, we can see with this show usage of node and XDSM, we can see where exactly in our MDO system is this lift parameter also used. And if we click on this and hold it, we can see that there's only one place in the MDO system where it's actually used, and it's between the error analysis tool and the structural analysis tool, as we have already seen before. Okay, now that's the tree view. Let me also quickly show you the list view, which basically gives you the entire list of your MDO schema. And again, this can be filtered if I, for example, only want to see all the nodes that belong to the geometry. I can type in geometry here and see only those nodes, and also inspect them in the same way that I did for the tree view. So as you already know, this layout that we're looking at right here is the XDSM, the Extended Design Structure Matrix. And how it's read, it's basically that you have the tools or competence blocks on the diagonal of the view, and on the off diagonals you have the tool connections, also called edges. On the right hand side we have the forward connections, and on the left hand side you have the feedback connections. Now in this case, since this is just the tool repository and the tools are not in a specific order yet, feedback and feed forward doesn't mean anything yet, but later when there's actually a tool order, this will mean how the workflow will be executed. Now we can have a close look at the connections between the different tools by right-clicking on any of those edges. I will now have a closer look at the one between the error analysis and the structural analysis, which basically is only one connection, the lift force. I can get some information about the node. I can also get the variable tree and the variable list according to this node. And I can also, if I think this variable connection shouldn't be there, I can also manually delete it here. In this case, I don't want to do that actually, because I know that this connection is correct here. But just hypothetically, to show you how it would work, I can quickly go through it. So let's just click on this variable deletion, and what we have to do now is we have to specify the full XPath of the variable that we would like to delete. And to get that XPath, I simply can open, for example, the list view and copy that XPath to the clipboard. And then go back to that delete option, insert the variable XPath, and if I click OK, this would be gone, the edge would be gone, but I don't want to do this as I already said before. Alright, so we have completely set up the tool repository now. But as we can see, the tools are rather arbitrarily ordered, and there's no workflow process that we could execute yet. The next step is therefore how to get from the tool repository to an executable workflow. To do that, we first have to set up a problem formulation. This means we have to specify which of the tools from our repository we would like to include in our analysis, and which of the variables from our data schema are the objectives, design variables, constraints, and so on for the analysis. That way, we are setting up the so-called fundamental problem graph, or FPG, of our MDO system. So to start defining an MDO problem, I will go to this drop-down menu Graph Manipulation, go to FPG Manipulations, and then I have several options to manipulate my graph and define my MDO problem. Now the first thing I would like to do is I would like to copy the current graph for further manipulation. So I still keep the results from my repository connectivity graph that I'm seeing right now. And if I copy this graph, I will have to specify a name. I will call it FPG simply, and it's the fundamental problem graph of our supersonic business jet example. If I click OK, we actually see that we are now already in this fundamental problem graph, and we can actually start defining the MDO problem now. So one of the things I would like to do is I would like to get a more reasonable function order into my process. Right now, as I already said, the tools are quite arbitrarily ordered. We could do that by actually right-clicking on any of those tools and changing its competence position in the graph. But that would mean that we would have to do everything manually, and it would take some time. And CutMouse already comes with a function that does that automatically for us. And what it does is it reduces the number of feedback connections as far as possible, because feedback connections always mean that there has to be an iteration, which means we have to execute our entire process all over again. So when we click on that Get Possible Function Order button, we will see that there are different options to sort the competences. There's, for example, single swap or hybrid swap or others, but basically they should all have the same result. So we will be using the single swap algorithm for now. And once we do that, we can see that the tool order we're getting is much more reasonable than before. We have the propulsion analysis, structural analysis, and the error analysis in the top. We have the performance analysis somewhere more downstream, and also the mathematical functions somewhere in between and in the end. Another thing that we can do is we can get rid of the competence blocks that we don't want to include in our analysis. We can do this by either right-clicking and deleting the competences manually, or we can go to the FPG manipulation bar and removing design competences by selecting them. And then Catmos removes all those competence blocks from our MDO problem. Now, since I don't want to do that because I think that all the competences should be included in the analysis, I can go a step back, and as we can see, all the competence blocks are back again. Another thing we can do is we can merge competence blocks that belong together to a single competence block. In this case, in our supersonic business jet, we however don't want to do this. We just leave the workflow as it is now. Now the next step is we have to define which of the variables from our data schema are important for our specific MDO problem. This means we have to specify design variables, constraints, objective functions, and quantities of interest. In this small example, I would like to keep it simple. Therefore, I just want to set up a small problem in which we would like to vary the flight altitude and flight Mach number of the aircraft and investigate its effect on the range the aircraft will be able to fly. So the altitude and Mach number will be the design variables, and the range will be the objective function. And to do that, I can simply go to the data model in the list view and search for the variables that I'm looking for. Let's look for the altitude, which is h in our data schema, and I will pre-assign the altitude as a design variable. And let's say our aircraft usually flies at 10,000 meters. Then I will set the upper bound to 12,000 and the lower bound to 8,000 meters. The second design variable is the Mach number, which I will also pre-assign as a design variable. And let's say our aircraft usually flies at 0.8. Then I will set our upper bound to 0.85 and the lower bound to 0.75. Now we have to specify the range as our objective function. I will pre-assign that as a objective. And now we have the three variables pre-assigned. To actually assign them, we need to go to the graph manipulation bar again. And then we go to the FPG manipulation and assign the parameter roles with a Catmos function. And we can actually see now that these variables have been assigned by going to the data model again, and this time we will show the list view as a row levels categorization. And then we can see the three variable roles of the Mach number, range, and altitude, two design variables, and one objective function. Now actually in this case, since the range, as we can see here, is given from the performance analysis to this FR tool, which is basically just a mathematical function that processes this value and gives it back to the outer world, we have to include this range parameter into the parameter roles as well. So let's see, we have this value R, and we also assign this one, and in this case we assign it as a quantity of interest. Okay, go back to the assign of the parameter roles. Now that we have defined what kind of analysis we would like to perform, we have to specify which of the competence blocks are playing what role in this very analysis. This is automatically done by Catmos in the background, and we simply have to click the button Assign Problem Function Roles. Okay, so we're almost done. The last thing we can do is, as we can see on the left side, we have a lot of variables going to the outer world that are actually not interesting in our case right now. The only thing that we wanted to focus on was the range that is in the left side of the graph here. That's coming from the performance analysis. All the other variables that are written here are actually not used in our case, so we might as well get rid of them. And I will do this by going to the FPG manipulations and remove the unused outputs. There's also the option to remove collision parameters. A collision is defined as something that happens when two competences write the same variable at the same time. And this is not allowed in an MDO system. So you could specify here which of the competences should actually write the variable and which should not. Another way to get rid of those collisions is the option Make Variables Valid that we can see in the top. In this case, CutMOS will automatically create two instances of the variable, one for the one competence and one for the other. Okay, let's remove those unused outputs. And then I get asked whether I want to clean up the entire graph afterwards. So this will remove all unused competences as well. But let's first not do that and see what happens. Okay, as we can see now, all the unused outputs are gone, but we have a lot of loose ends, such as this, and those two competences back down there. So we might as well just delete them because they have no effect on the MDO system right now. Now I could have also removed those competences automatically by just clicking the yes on the question whether I wanted to remove the unused competences as well. But now I will just have to remove those competences manually. Now let me quickly do this, and I will go to PG, remove design competences, and exactly have a look. It's this, that one, and this tool. Click on them and remove them. Yes. And now we can see again that there are some additional unused outputs that are here that we still have to get rid of. So I will remove these two. Okay. Now the fundamental problem graph is completely defined, and we can proceed with the next step, which is to find a suitable solution strategy for the design problem. In our case, I would like to set up a design of experiments, or DOE, for our problem formulation, which is basically a simple parameter study where my design variables are changed and my objective functions and quantities of interest are the output. So we are varying both the Mach number and flight altitude and investigate their effect on the range that the aircraft is able to fly. And to set up our MDO architecture, we will have to go to the MDPG manipulations, and first of all we can copy the graph again before we start actually defining the MDO architecture. That way we keep the fundamental problem graph. And I will just call that SSBJ MDPG, or even better would be DOE, since we're doing a design of experiments. And now we can select a MDO architecture, which will be the design of experiments. There are a lot of other architectures that could be defined, the MDF, IDF, Bliss 2000, and many more. But I will not go into detail about what those are. So let's just select the converged design of experiments for now, which means we will also converge on the variables. The coupling decomposition, there are two available. We will use the Gauss-Seidel one. And then we also have to set a DOE method. There are three available, and we will use the Latin hypercube design now. And then as a final step, we can impose the MDO architecture. And now that we have done this, we can see that there's a DOE block in the top There's a converter block which iterates over the variables, in this case drag and lift. And we can see in the top our design variables altitude and Mach number, and in the bottom left we can also see our quantity of interest, the range of the aircraft. Alright, so we have seen almost all the capabilities of the MDO system interface. If you want to do more advanced manipulation of your MDO problems, this is also possible by uploading your own CutMos script. You will have to code that yourself in Python, but it gives you the opportunity to do whatever you like, even things that we might not have thought about including in this interface. So just click on Upload Custom Script, and you can do that. You can also download a template file, which is a Python file, to your local storage system. And if you save that one, you can actually see how it looks. There's only a very small example given. I can quickly show how it will look. But basically you will have to do all the coding yourself. So here's how it looks. And that way you can perform all the graph manipulations that CutMos allows according to what you would like to do. And now we can also have a look at the execution order of the process that we just created. And to specify what exactly is happening in each of these competence blocks, for example our error analysis tool, we have to specify the tool metadata in detail. We can have, for instance, either a local tool that can be executed via command line or a remote tool on some other person's computer somewhere else. Eventually, we will have to specify this information for all of the tools in our MDO system. Okay, so we're almost at the end of this part of the demo. The last thing we need to do is to move from this problem formulation to an actually executable workflow with real tools. What we see here is only a representation of the actual workflow. But what we can do to get an executable workflow is we can export this MDO system as a commandos file, which can then be processed by a workflow engine platform such as the remote component environment from the DLR or Optimus from Noesis. This will be explained in the next part of the demo. Just let me quickly export this MDO system as a commandos file, and we're almost done.
Now that the MDO knowledge has been formalized in commandos, it is time to convert it into something that can be actually executed. And one of the platforms that allow for this step is Optimus, developed by Noesis Solutions. Optimus is a process integration and design optimization platform that, thanks to a series of scripts developed within AGILE using Python, can parse the commandos file and extract the critical informations required to create an executable workflow. Simulation results can then be analyzed using ID8, a cloud-based post-processing platform also developed by Noesis. Optimus is a commercial PIDO platform that is centered about its interface, that allows to formalize the engineering problem in terms of design variables, analysis elements, and results. Any user is free to use its own analysis software or integrate a commercial one by means of standardized interfaces. Once that the workflow has been created, it can be used to perform multiple analyses ranging from design space exploration, optimization, single and multi-objective, as well as reliability assessment. And when the simulations are done, the results can be loaded and post-processed internally without need for additional tools. In order to be set up, Optimus relies on a standard installer available for both Windows and macOS. In the final step of the installation procedure, we can select the interfaces for the software that we are going to use in the future. Customization options also include additional optimization algorithms and tools for parallel execution. During a simulation, workflows developed with different platforms and hosted on different machines need to be able to exchange data. The form used for the data exchange is the CPAX file, and the technology that makes this exchange available is bricks created by the NLR. In order to be more easily used in Optimus, bricks has been embedded into dedicated interfaces that expose all the functionalities related to both single and multiple execution tasks. Bricks interfaces can be added by simply copying them into the installation folder that holds the interfaces for the commercial software. Upon restart, Optimus will display the bricks interfaces on the right side of the graphic user interface. Bricks takes care of three fundamental aspects of the collaborative workflow. The first is the setup of the task and the upload of the analysis request. At this stage, the CPAX file is uploaded on the neutral domain. When the tool specialist is ready and begins the analysis with its tool, the bricks receive interface at the beginning of the workflow will download the data. And similarly, when the analysis is done, the bricks send interface will send the results back to the neutral domain, from where the workflow that requested for the analysis will retrieve them. Here we can have a quick look at the bricks interfaces as integrated into Optimus. The bricks job 1 is responsible for the creation of the task, and as you can see, in its field it's possible to set up who is going to receive the analysis request and where the data will be stored on the neutral server. Whereas in the receive and send interfaces used by the tool specialist, it's only possible to set the name of the task that is going to be downloaded and executed, as well as the remote folder. The workflow in this picture represents the Optimus implementation of the first collaborative MDO created during the first design campaign. It was assembled by hand, a procedure that turned out to be extremely error-prone and time-consuming, and in spite of the limited number of variables that entails, any operation such as upgrade or even just maintenance proved to be a non-trivial task. Similarly, during the second design campaign, more complex workflows, also able to couple with the surrogate models, continue to be constructed by hand, while the materialization technologies were being developed. The third and final design campaign has been mostly entirely managed using automated workflow generation and materialization. Instead, the materialization of an MDO described in a commandos file is a process that requires a minimum human effort as it is mostly automated using dedicated scripts. In case of commandos to Optimus conversion, 5 steps have to be performed. At first, the commandos file is read in order to access the list of all the variables that are in the problem, both in terms of input and outputs, all the disciplines and their characteristics, and the connections among them that define the architecture of the problem. Then some Optimus-specific information have to be added to the neutral-specific structure of the commandos file. Then the real materialization can begin, working bottom-up from the disciplines created as templates and the intermediate connection level that is required by bricks. The final level created is the MDO itself, which is automatically connected to the lower levels. Then the only action that is left to the user is the association of the MDO workflow with one or more analysis methods like DOE or optimization. Usually, within the Agile project, the materialization scripts are hosted on a cloud and accessed through Keychain. In this case, I have them on my computer, so I will use them directly. The 3 functions called in the script read the commandos file, convert it into something that is more Optimus related, and finally perform the materialization with the created information. The first thing that I have to do is to verify that the commandos file that I want to materialize is the correct one. The proper tool to explore a commandos file in all its details is Vistom, but in this case I'm looking for high-level information that can be retrieved using any kind of editor. Here I can see that this problem describes the supersonic business jet optimization, is being created by income. Usually in commandos, the disciplines are just described in terms of inputs and outputs, but in this case, to find the list of commands required to perform the analysis. Therefore, the MDO that I'm going to materialize is going to be completely functional, but in terms of MDO and disciplines. The materialization in this case is almost instantaneous, and in the worst case tested so far, involving thousands of variables, it took a few minutes to completely generate the MDO. At the bottom of the screen, we can see a list of debug information that have been printed, and this includes the list of disciplines created, as well as the list of all the elements that have been added to the created workflows. Now I can open and inspect the MDO that I've just created. As expected, there are 3 disciplines inside a convergence loop. And 1 outside, which is the performance evaluation. I can also check that all the design variables are as expected, but in terms of names, minimum range and maximum, as well as nominal value. The same applies to all the other input variables required for the convergence loop. And the parameters, variables that have fixed values, therefore they are not part of the optimization or any other method associated to this workflow. The disciplines are invoked through a structure which is called Optimus in Optimus, where the variables in the MDO are mapped one-to-one with the variables in the discipline. This association is done automatically during the materialization, and is one of the most time-consuming and error-prone steps in the MDO. In a typical Agile MDO, this list of variables could have hundreds, if not thousands, of elements. The final components of the MDO are the constraints, which have been parsed in the commandos file, and materialized in terms of both formula and minimum and maximum values, as well as the objective. A similar inspection can be performed for disciplines. They all share the same structure as they are materialized from a template, which is customized according to the list of inputs and outputs for each specific discipline. As you can see here, there are 11 inputs that have a non-specified maximum and lower value, as this information is not exploited at this level. Every discipline executes the commands that were specified in the commandos file. This is possible only because all the disciplines are analytical tools. In a more realistic scenario, every specialist would have to customize the tool according to its needs. Finally, the list of outputs. Now that we have verified that the workflow is formally correct, we can associate it to one of more analysis methods. This could be a nominal execution, a table of experiments, a DOE exploration, or more complex single or multi-objective optimization. In this case, we select a local optimization algorithm from the list of all the possible methods, and we deselect from the list of inputs the parameters in order to have them retain a fixed value. We can then verify that all the outputs are selected for the analysis, and the constraints have inherited the boundaries set from the original workflow. If need be, we could edit these values. Now that the simulation is started, the only thing that we have to do is to wait for its conclusion. And in the meanwhile, we can use the monitor function to check the progress made so far, as well as to gain some knowledge on the problem characteristic, knowledge that will be expanded during the post-processing at the end of the run. When the simulation is over, I can load the results and post-process them. This is possible both through summaries and tables, as well as more advanced technologies that are based on graphs. In this case, I can check that all the variables are subjected to changes, and that the values highlighted in orange means that a constraint has been violated. As expected, the objective function has been reduced. I can quickly check the optimal design point, and in this case, orange on the inputs indicates that this is a boundary solution. Additionally, I can check all the outputs for the best and the first experiment, in order to discover that the original point, the one that I used to start the design, was actually non-feasible. We could perform more post-processing here in Optimus. Instead, we will save and share the results using ID8. ID8 is a cloud-based instance, and every member of the AGILE consortium have been provided with the credentials to access it. This can be done through keychain or manually, as in this case, and it is compatible with the most widespread browsers. Once that I'm inside ID8, I can see the list of all the projects that I've already loaded. I don't want to use one of these, but I will import the one that we just ran. The system now asks us to identify what are the inputs and what are the outputs of these methods. And now that the project has been successfully uploaded, we can select it for post-processing. All the results exploitation methodologies that are available in Optimus can also be exploited here. We just have to select what is the method that we want to study, but it's also possible to merge simulation coming from different analyses and explore them all in one take. Here we have a summary of the results that we already explored in Optimus, but we can add a new widget to perform, for example, the correlation between inputs and outputs in terms of Pearson coefficient. That for clarity is reported both using a color schema and the numerical values. Additional post-processing technologies include scatterplot, both 2 and 3D, histograms, bubble plot, parallel coordinate, and Pareto front evaluation.
In this part of the video, we'll look at how you can automatically generate executable workflows in the RCE workflow software using commandos files. Let's start with a small recap of the situation that we are in. In part 2 of this video, we have seen that using Vistums and Cosmos, we can create different solution strategies for our design problem at hand. And we can store these solution strategies in commandos files. And now what we'd like to do is we'd like to open these solution strategies in a workflow engine such as RCE in order to be able to press the play button and really run the solution strategies that we have created. Okay, so let's say I have these commandos files available which were created by Vistums. I have a DOE strategy, 2 MDA or convergence strategies, and 3 different optimization strategies. And finally, I have a file available that contains some nice starting values for my supersonic business jet design. Let's now go to RCE. And if we have RCE open, we first need to install the Commandos plugin and also a plugin called Bricks, which I'll tell you a bit more about later. In order to do that, we go to Help, Install New Software, and in the Work With field, we have to use this link over here. And then we will see here that we have additional components for RCE called Bricks and Commandos. So here I have my RCE installation with the Commandos plugin installed. And if we click the plugin button, we can choose a Commandos file to import. Let's first have a look at an MDA strategy with a Gauss-Seidel convergence. We simply click the Commandos file, and we can also choose an input file which provides us with some nice starting values. This is, in our case, the SSBJ base file containing some nice starting values based on the schema that we have. We place this new workflow in the Agile demo video folder. We press finish, and now automatically the workflow is generated that we have actually specified in Vistems. So here we now have a workflow with a converger block in RCE. We have the different tools that we are using, so we have the structures, aerodynamics, propulsion and performance tools. And in this case these are actually tools that have been integrated inside RCE already. So these are now local tools that we can execute if we press play on this workflow. And in the lower right we have our mathematical relations that have been specified, and in that case we don't really need a tool, but the mathematical relations are simply made into small Python scripts in RCE, and we see here that we have the equation that has been specified automatically generated inside RCE as well. So this is a convergence doing a Gauss-Seidel approach, meaning that the tools are in sequence. Now we can also quickly reconfigure our workflow, and we take the Jacobi approach for the convergence. We set the same input file, and when we finish we get a new workflow now, and in this case our tools are executed in parallel inside the converger block. And for the rest, this workflow is of course the same as the Gauss-Seidel convergence one. Now we might say we want to do a design of experiments. So again we open our Commandos file using the interface. We select our start file here as well. And with the push of a button we get our new workflow, and in this case now we have our design of experiments block, which is around the converger block, because for each experiment that we do we'd like to converge the design and then go to the final tools to get the final outputs and then go back to our DOE. And in Vistems we have specified that we'd like to do a Latin hypercube design, and all these details has been taken from the Commandos file, and the DOE block is automatically configured in the right way with 10 desired runs. And over here we can also see the lower and upper bounds that should be used for the different design variables. Finally, of course, we want to do optimization, and let's say we first want to try out an IDF approach here. So in that case we take our IDF Commandos file, and when we open that in RCE we now get a fully configured optimization workflow based on the IDF strategy. So here we now have all the tools in parallel again. There's no converger because in IDF the convergence is handled by the optimizer. And so again we have a fully configured workflow by the push of a button, and we can press the play button here in order to run really the optimization. Then if we want to reconfigure the IDF to the MDF strategy, we have another Commandos file available. We do an MDF with a Gauss-Seidel convergence strategy, and using the same settings we can open this file, put it in our Agile demo folder, and directly instantiate the MDF workflow that we'd like to use. And so here we see we have an optimizer, and inside the optimizer there's the converger that has been configured. We converge the couplings between the different tools, and after convergence we go to the constraint and the objective functions. As I already mentioned, the tools at the moment are now local tools, which we can see by looking at the tools that we have available. We have the aerodynamics, performance, propulsion and structures tool inside RCE, and it's using these tools now in order to execute the workflow. But in a real collaborative optimization situation, as we have seen in part 1 of this video, We could also have the situation that these tools are actually not locally available but can be provided by different partners. In that case, what we'd like to use is Bricks. So Bricks is a software elaborately explained in the Optimus part of this video, but we can use it in order to execute tools that are available at different locations around the world. And in RCE we can also automatically instantiate workflows using these Bricks components. So we have a second commandos file available, and in this commandos file the tools are not specified as locally available tools, but they are specified by providing the remote component information. And if we open this commandos file, we will get a slightly different workflow because the local tools have now been replaced by Bricks components. And for Bricks we need to provide some SMTP information so that it also knows how am I going to send the information to my colleagues. If we provide that information, we can now again open a new workflow, and in this case we see that the tools have been replaced by these Bricks components, and we see that the structures tool is now run by the DLR. We have Air Innova providing the aerodynamic analysis, SIAM is doing a propulsion analysis, and finally Bombardier is providing a performance analysis. And if we look inside these components, we see that they are not really tools, but they are simply Bricks components, and based on the commandos file all the settings have already automatically been written to these components. So here we see that Pierre Davide Ciampa from the DLR will be running this tool. So when we execute this workflow, he will get an email to also start his tool on his side so that we can perform the optimization. So that's the creation of executable workflows based on commandos files in RCE in a nutshell. In this part of the demo, I would like to show you how you can create an OpenMDAO optimization model and execute it through the OpenLEGO package based on a single commandos file. But let's first start with a small conceptual overview of what I'm about to show you. So we'd like to use the OpenMDAO framework, which is under development by NASA, in order to run our optimization. And as we've seen in the second part, we have a commandos file that contains a full description of our strategy to perform this optimization. So we need something in between these two in order to achieve this. This is why the OpenLEGO Python package has been developed. This has been developed by Daniel de Vries, a student from TU Delft. The nice thing about this is that both OpenLEGO and OpenMDAO are fully developed in Python. So we have a nice Python framework here that we can use to run our optimization. And in order to install these things, we can simply do pip install OpenLEGO. Let's now have a look how we can create OpenMDAO models based on different commandos files in order to do convergence, design of experiments, or optimizations. Okay, so let's start over here. I have an Agile demo video folder, and inside this folder I have another folder which contains different commandos files. So here we have 4 commandos files that describe a design of experiment strategy for the supersonic business jet. We have 2 different multidisciplinary design analysis strategies using either a Gauss-Seidel or a Jacobi converger. And we have 5 different optimization strategies that we can use in order to optimize our supersonic business jet. The other folder that we have is our database folder, which contains the 4 different tools that we can use to analyze our supersonic business jet. So the aerodynamics, performance, propulsion, and structural analysis. Then I already created an output files folder, but this one is still empty. And we have our SSBJ base file. This is a file containing some starting values that I will get back to later. So let's open our IDE. I'm using PyCharm here in order to create and run Python files. And inside the Agile demo video folder, I will create a new Python file, which I will call demo script. So what we'd like to do now is we'd like to open this commandos file in order to create an OpenMDAO model that we can execute. And in order to do this, we actually only need one import statement, because from OpenLEGO we need to import the LEGO problem class. So the LEGO problem class is actually a subclass of the problem class from OpenMDAO. And in order to instantiate our problem, we have to provide some inputs to the LEGO problem class. First input is of course the commandos file that we'd like to use. So we store these files inside the commandos files folder. And let's say that we start with an MDA, so we just want to converge our supersonic business jet. We take this file to build the model. Second input is the knowledge base path, so this is actually the database that we're using where we can find the different tools. Then we can provide a data folder to write some of the outputs. And we can provide a base XML file. So this is a file that will be created when the program has executed. In this case the MDA. It will write all the results to one base file, and that file will be an XML file that is called output MDA in this case. So this is how we create our problem, which is actually a LEGO problem that creates a LEGO model, and both are subclasses of the OpenMDAO model class and problem class. So we of course like to know and see a bit more what's going on, so we can use the model view from OpenMDAO, and we could say we'd like to open that directly in the browser. So if we run this, the browser will be opened automatically and we can inspect our LEGO problem, or actually this is the model that has been created that belongs to the problem. And we see here that we have a converger or a converger group that contains the structural, the aerodynamics and the propulsion analysis. And we have some other functions that were created in Vistoms. We have our performance analysis outside the converger, and here we also have our range equation, which is actually the objective of our optimization later on. And we can of course inspect this full model in detail in order to make sure that we have instantiated a LEGO problem that is actually valid and that we'd like to execute. So in order to execute it, we would simply use run driver, and this would then execute the problem. But before we do that, we would like to make sure that we have some nice starting values. So in order to do that, we use a special method called initialize from XML, and we initialize now using this SSBJ base file. So the SSBJ base file was the file that was already in the folder, and if we open this file, we see that it already contains some starting values for the different values that are used by the supersonic business jet tools. So these values are now automatically written to the model that is executed by OpenMDAO. So if we run driver, and now we press the run button, and here below in the log we see now that the converger has successfully executed, and it was able to converge this design in 0 iterations because the design in the SSBJ base file is already a converged design actually. And if we'd like to see some more results, we can use the collect results method, and this method looks at the type of analysis that is given in the commandos file, and it will give us the results that we are interested in for these kind of runs. So in this case we're doing a convergence, so it will give us the quantities of interest that we are interested in based on what we have provided in Vistoms as the values that we'd like to see. So that's a multidisciplinary analysis. Now we can also quickly move to another type of strategy by simply changing the commandos file that we provide as input. So another option that we have would be to do a design of experiment that we have configured in Systems, a design of experiment doing convergence of each design using Gauss-Seidel, and we have provided the different samples in a custom table in this case. So if we replace the commandos file for this one, then we want the output to be output DOE, and now the rest of the script stays the same. We can simply run it, and now in the log we will see that it's doing convergence for different samples that we have provided, and it's collecting the results in the end. And what we see now is that for each case it will provide us with the design variables of that case and the quantities of interest for the outcome. So within the commandos file, actually 10 different cases were provided. So we see that over here, and it's printing all the cases for us. So that's very nice. And then finally, of course, we would be interested in doing optimization. So we had different optimization strategies that we created in Systems. And let's say we start off with an MDF using a Gauss-Seidel convergence scheme inside. So if we replace the commandos file for this one, then we also would like to change the output to MDF Gauss-Seidel, and we will initialize using the same base file. So if we press play, we will now see in the output that it's performing the optimization, it's doing the convergence for the different iterations, and in the end the collect result functions gives us the final design that was found, because that's the optimal design, where this normalized range value has been minimized, but actually the range of the supersonic business jet is maximized. We can see the design variables and the constraint values for that optimal design that was found. Another nice thing is that since this problem object is a subclass of the OpenMDAO problem object, we can also use typical OpenMDAO settings still. So we could use a typical one like this, which would be used in order to turn on the debug printer if you want to have a bit more detailed idea on what's going on. And in the same way, we could change the output of the solver that is shown. So we can set that to 0, for example. Let's now say that we'd like to do an IDF strategy. So we change everything to IDF. If we press play now, we would get the output for the IDF strategy. And here we see now that the debug printing has been turned on. So we see what the optimizer is doing in every iteration. And at the end, the collect result method gives us the final design that was found. And as we see here, with IDF, some additional design variables have been added because the couplings between the tools are not converged using a converger, but they are converged using the optimizer. And we also get additional constraints because we have to make sure that there is consistency with those couplings between the tools. So in a similar way, we can now move also to other strategies, and with OpenLEGO also some distributed optimization strategies are available, such as Bliss 2000 and collaborative optimization. Finally, we will see in the folder that different outputs have been created. Within the output files folder, the different case readers are also stored, so we can still access the data after the execution. And the different models that we have opened in the browser are also stored here in the output files folder. And over here we also see the output, the final output of the different executions. So here we will find an XML file with the optimal design using the MDF Gauss-Seidel strategy. And so now we have here an XML with all the entries, all the values for this optimal design. And of course this XML file can now be sent around quite easily, and other people that might have tools available that can also operate on these kind of files could do additional analysis on this optimal design that has been found. So this was OpenLEGO and OpenMDAO using commandos files in a nutshell. Of course, there are many additional options and methods that have been provided, but I would suggest that you have a look at the OpenLEGO repository in order to find out what else you can do using this approach. Let's end this video with a short recap of what we have seen throughout the different parts. So in part 1 we started off by creating a collaborative MDO system. And this meant that we needed to adopt a central data schema in order to read and write the data for every tool. In aircraft design we can use the CPEC schema to read and write typical data used in the conceptual and preliminary design stage. Once we have this collaborative MDO system, in part 2 we wanted to visualize that system, and we've done that using the Vistems package. So with Vistems we can inspect our collaborative MDO system, and furthermore we can also manipulate it in order to define our MDO problem and our MDO solution strategy. Under the hood, Vistems is using the graph-based approach that has been developed in the Python package called CapMos. And when we have our solution strategy in Vistems, we can store it as a commandos file. Commandos is short for the common MDO workflow schema, and like CPEX, it's an XML standard, but in this case we can use it to store the formulation of our MDO solution strategy. And if we have stored this MDO solution strategy, we can now open it in different workflow packages. And this is what we have shown in part 3, where we saw that we can open the same commandos file using Optimus, RCE or OpenMDAO through the OpenLEGO package. And in each of these 3 workflow softwares, we can now open our solution strategy and run it in order to get our results. Finally, we also saw that in order to create truly collaborative workflows, we implemented some of the tools using bricks. So with bricks, we can really execute tools that are located on different server domains, and we can really have one master workflow that calls tools from different partners all over the world in order to perform our optimization. Finally, the commandos file can not just be used to store our solution strategy, but we can also use it to store other stages of our MDO systems. So in part 1 we could also have stored our MDO system using the commando schema and then open it in Vistems using a commandos file. And furthermore we could save our MDO system that we have in Vistems at any time as a commandos file and maybe use it in other types of tools or applications that we might have. From this overview we can also see the power of the Agile paradigm, which is that we now have a fully automated chain to go from the definition of our collaborative MDO system to creating executable workflows in a range of different softwares. And thanks to this chain it also becomes very easy to reconfigure our MDO systems, because generally in design projects we don't do one execution, but we do an execution, we get some results, and we see that we have to adjust our MDO system in order to improve our design. Furthermore, with the commando schema, we can also easily add other applications to our paradigm in order to support the design team with different tools. Hence, we have really become agile. Thanks for watching this video, and if you'd like to know more about certain components of the agile paradigm, you can find additional information at the websites that are listed on this slide.